because we didn't do a resistor and inductor in parallel like this. Not that we couldn't, it was just, this isn't a circuits class, but it's a good step towards a circuits class. It gives us the fundamental physics of Faraday's law and then why we care about Faraday's law. But I better read the circuit here because I'm concerned it might be harder, depending on what they ask, than what we did this semester. But I don't think so. I think they just asked for like first close and stuff. What is the current in the inductor when the switch is first closed? Great question. We talked about this. How do we treat an inductor when it is first closed? Right, as an open circuit, right? There is enough back EMF to stop the current. That was our whole conceptual discussion before we got into the math here. So when you first close the circuit, and they don't label it as question A, but I'm going to put question A. Let me call this current in the inductor. So current in the inductor equals 0. So what is the current in the inductor when the switch is first closed? That's what the back EMF will do. And of course we also asked the other side of this. How do you treat an inductor after a long period of time? Yeah, as if it is just a wire, because now things have settled out and there's no more changing. You only get an EMF when there is change going on. And I think that's the next question. After the switch has been closed for a long period of time. Okay, so after it's been closed for a long period of time, let's talk about this for a second. You could just think of this as a wire. In other words, there's no voltage change, right? Because there's no current change. So by the way, if there's no voltage here, how much would there be here? 0 volts, right? They're in parallel. So how much current would be going through here? 0. And so after a long period of time, the current is just going like this. As if that's not even there. And if that's a wire. So after a long period of time, this just looks like 25 volts, 10 ohms of resistance, and back. Oh, that's an easy one. I'll call it part B. What is the current then? Yeah, it's just 25 divided by 10, 2.5 amps. All right. So far, nothing too hard, but it does require our whole idea of Faraday's law. What happens right when you close the switch? What happens after a long time? Here's a good one. What is the current as a function of time when the switch is opened after it has been closed for a long period of time? And I hope this looks like an inductor being de-energized. Remember we talked about what is the current while you are energizing the inductor, and then what is it while you are de-energizing the inductor. And so I'll call this C. We said that the current in the inductor was the initial current, because remember, it doesn't want to change its current. It will produce enough voltage on its own. So once you are disconnecting it, once this has been closed for a long period of time and you open it, wouldn't that be like thinking about the circuit with all this gone? And so this already had a current of 2.5 amps. What's going to happen? Right, it's going to want to start changing, but as it's changing, it produces a voltage. And so the current's going to go around like this. And now you're going to have a decaying current as the current gets de-energized out of our inductor. And so we said the currents would decay away as opposed to building up. So on the last test, practice test, an hour or two ago, we saw the current building up. Now we're seeing the current decay away. The only part on this is to make sure we connect these numbers because this then is the initial current. So that's where part B comes back into play. What is the current after it's been going for a long period of time? And now it's going to decay away. And maybe I should write this as L over R for the decay constant in our inductive circuit. And so this would be 2.5 times e to the minus, and in this case it's decaying away only through the 25 ohm resistor. The 10 is out of the picture once that has been opened, so this would be 25T over the inductance, which would be 0.07, which we can simplify if we want, but given our time frame, maybe I'll leave it there and say, yeah, closed out as a function of time, yeah.
So could you explain again why the circuit reduces down to the one in part B after a long period of time?
Yeah, okay, so let me start again with my picture here. After a long period of time, the inductor acts like a wire. Now let me pause right there. Are you good with that phrase? Okay, so after a long period of time, the current is not changing anymore. And since the voltage on an inductor is minus L di dt, if there's no more changing of currents, there's no more voltage here. All right, so if the voltage from here to here is 0, that means the voltage from here to here, I'll call it voltage on the resistor, is 0, which equals to IR. So how much current must be going through the resistor? 0. And so it is basically saying this isn't here because it's free to go through this path. And in fact, this inductor, the flux from the inductor has stopped doing its thing, and so now it's just a wire. And so that's how that circuit came to be. And so then it's just a V divided by R after a long period of time. All right. And maybe we should try, here's another toroid one. And this sounds like a toroid with another wire inside moving. And I know there's flux inside and there's moving. This is going to sound an awful lot like a Faraday's Law one. But let's read it here. Number 3 says we have a toroid which consists of 500 turns, has a rectangular cross sections with the dimensions as shown. There's a lot of stuff up there. A single loop of wire which measures 2 centimeters by 1 centimeters right here and has a resistance of 5 ohms is traveling with a constant speed of 20 meters per second to the right, through the right cross section of the toroid from left to right. If the current in the toroid is 25 amps, what is the current, both the magnitude and the direction, when the loop is at the center? Wow. And then the magnetic field from a toroid is, and now we have that again for the third time. All right, so this is the magnetic field, and they've got a much detailed picture there. So I'm going to go ahead and try and draw just the cross-sectional area of it. And so over here, here's that rectangular cross-section. And here's this little rectangle that is moving pretty fast through the center part. And maybe I should just ask you a conceptual question. Is there a change in flux? Yeah, why? Yeah, the field changes, doesn't it? And so as we measure from the center here, and what symbol do they use for that distance? It looks like X. So let's just call to this is X. And so this X is now moving. And the length of this rectangle is 0.2. The height of it is 0.1. And maybe the thing to do first is to realize this is Faraday's law. And there is a change in flux because according to the equation for the toroid, the field gets weaker as it gets further away. And so this rectangle, when it is right here, has a lot of flux, and when it gets over to here, it has less flux. So maybe before we even do the numbers, let's do the directional part of this. And so I'll get ready here with my Lenz's law in my right hand. They tell me that the toroid has 25 amps, and it looks like in the picture that's kind of been cut off a little bit. I think Don was just trying to save space. But can you see this part right here where the current? So from that alone, I'm going to just take my right hand and curl my fingers, and my thumb is pointing out. And so the flux coming from the toroid is out towards you, which is, I'm sure, why there are little dots right here. And so these little dots are saying field is out towards you. So when this little rectangle moves from here over to here, when it started over here, there was a lot of flux. Now, by the time it gets over to here, there's less flux. And so Lenz's law says we want to oppose the change. So maybe I'll just say make up for that change. So we want more flux that way. So I'm going to take my right hand and put my thumb out, because I want more flux out. And so I would want current to go, I'll stand on this side so you can see better, but I would want current to go around in a counterclockwise direction. And so I think that's what these little arrowheads are on this little loop. They're trying to represent which way would the current go, because it opposes the change. I'll say it again. It doesn't oppose the flux. It opposes the change in the flux. And so the flux is being reduced, and so it wants to add back to it. So that's why I'm going to point my thumb out to add back to what's being lost. And that's why my fingers will then curl in a counterclockwise direction. All right, so I got this part. I got the direction, counterclockwise. There's the direction of the current. And of course, the magnitude of it is where this math comes into play. And so I started to write down the math and then said, well, now that we got the concept, let's get direction. I'll start with the number of loops I have, and I should say number of loops in the secondary. And the toroid itself has 500s, but this has a single rectangular loop. And so this number here is a 1. And then I'll take the derivative of the flux through that rectangle. And of course, we did this one a moment ago, but it's worth doing it again. We did it to try to find the inductance of this toroid, but let's go ahead and say, all right, this will be the field from the toroid. And so there's the field from the toroid. And if I was adding the flux, and that picture's trying to show that maybe I would make a little rectangle here. And I would add up all of these little rectangles. And so the area would be this little tiny sliver, and I'm going to add up a bunch of slivers to get the whole rectangle. It would have a height of 0.01. I think that was the height, right? Yeah, 1 centimeter high. And its width would be dr. And like we did with the inductance, the angle would be 0 degrees, since the field is going out and the area vector is going out, so the angle between those is 0 degrees. And in my case then, I want to add up from this edge, which let me call it x, until I get to this edge. And so that would be the flux in this little rectangle. So I don't want the whole flux in the toroid. That's what we wanted last time when we were trying to find the south inductance. We wanted to know how much flux was in itself. But now I want to know how much flux is inside this secondary coil. So I want to make sure I'm adding up just what's inside of this rectangular one, not what's inside the whole toroid.
So would the bounds be like from x to x plus 0.2?
Yeah, so I would just put x to x plus 0.02. And of course, then it would depend on where x is, which of course is part of that question, because the question is saying, what is the EMF when it's right in its center? And so I guess we need to talk about what is x equal when it's at its center in just a second, but I'll just leave it as an x right now, because I do need something that changes with time. What changes with time, by the way, in this problem? Okay, so it is the x or the r, whatever you want to put in there here. But let me actually then do this integral here. And so the mu naught I will pull out. The n I will pull out. The I will pull out. There is no current that changes with time. It's just 25 amps. This, the height of the rectangle, 0.01, also doesn't change with time, so I can pull it all the way out. And then I also have downstairs the 2 pi, and so it looks like the only thing I'm left with is the integral of dr over r. And so this would be ln of x plus 0.02 over x. And then, what did I do with the derivative? Let me squeeze that in there. And then the derivative with respect to time. So let me just double check. I think I got all of that out in front. And then the stuff that does change with time is position. And so there's the integral, but I can't pull that in front of the derivative. In fact, maybe I'll even put in my numbers. Mu naught is 4 pi times 10 to the negative 7. The n, I think, was 500, wasn't it? Yeah, 500 turns. I'll put that one in. The currents, if I remember right, was 25 amps. Let me check that one. Good, 25 amps. And then I have a derivative. Ooh. And that does not look like an inviting derivative. Got a derivative of an ln, and then I got a chain rule that's got x's in the numerators and the denominators. But I can make it easy on myself. Let's change this to ln of x plus 0.02 minus ln of x. That's a much more inviting derivative. So I don't have derivative of a log and then a chain rule that has a quotient rule inside of it none of that looked too inviting. So I'm going to use the property of logarithms and a couple steps here. So this is 2 times 10 to the negative 7. This is 500. This is 25. This is 0.01. And now let me take the derivative of that, because the derivative of ln of x plus 0.02 would be 1 over x plus 0.02 plus the chain rule. And that would be the part that changes with time. How does x change with time? Let me take the derivative of this one, which would be 1 over x times dx dt. And of course, what would I call dx dt? Yeah, exactly. Isn't that the velocity? All right. So if I put in my numbers here, this would be 2 times 10 to the negative 7. This would be 500. This would be 25. This would be 0.01. And then this would be 1 over. And they gave me a specific position, didn't they? They said, what is the current when the loop is at the center of the toroid's cross section? All right. So the center would be at 7.5. And so going back 1 centimeter would make x equals 6.5. Right? And just be careful here with our details. X is measured from this front edge the way we did it. Makes me think we probably should have done the middle of it, but that's not the way I set it up. So, but the middle of this rectangle, at the middle of the cross section, would be 7.5 to here. So coming back would be 6.5. So 6.5, and then add this, make 6.5, I guess that's 8.5, right? So that's 8.5 times 20. That was the speed, right? 20 meters per second. And then this would be the 6.5 times the 20. And now it's just a matter of getting out the calculator and plugging these in. So right here would be 20 divided by 0.085, then subtract 20 divided by 0.065, and so that's about a negative 72, then times 0.01, then times 25, then times 500, then times 2 times 10 to the negative 7 comes out to be negative 0.0018. And this must be the EMF volts. Oh, and I guess I'm not quite done, because it says, what is the current in it? All right, so that's the voltage. To get the current, I would have to take the voltage and divide it by the resistance. All right, so I have the EMF, the voltage. What was the resistance of this wire? And then a resistance of 5 ohms. So that's equal.
Absolute value.
So divided by 5. Absolute value? Yeah, I think so. Hang on here. Amps. What? Absolute? Yeah. And so I guess I'm really like all the time doing that. And I'll do a positive. Yeah. And so we already said the current would be, what did we say it was? Counterclockwise. So we've already got the current counterclockwise, and then that would be its number. So we got its magnitude, and we got its direction. Ah, that was a good fun little derivative. I didn't expect that. So, but something's got to change with time, right? Whether it's current or position or angle, there's got to be something to change the flux. And so Faraday's law looks simple enough when you write it like this. But you can now see why we put a whole chapter just on that one idea. Because it's got an integral, a dot product, and then a time derivative all in it. And then of course we got to hook it with Ohm's law in order to answer the question, what's the current? Ah, good. Another RCL circuit here. Oh, are we almost out of recording space?
No, I just wondering how long.
Oh, I don't think too much longer. I'd like to finish this if you guys want me to finish it. Yeah, so I'll finish it. If you've got to leave, David, that's you fine. We can leave it up. Okay. If you got some more time, let me know if you have to go. We can, so there's a lot of things we could do. We could just leave it there. We could recruit somebody, or we could, yeah, he's still good for a little bit, or we can just call it good and we got most of it. Yeah. But I'll try to go quickly. How about that? But the last one here, or last two, excuse me, we've seen these before earlier on, so maybe I'll go a little bit quick. But this is that LCR circuit again. And so with the LCR circuit, we learned that, and I'll need to read it here, but I do know this, that the current would be the maximum voltage divided by the impedance times the sine omega t. That is coming from the power supply, which is the maximum voltage, and then sine, and it will be out of phase by some phase constant depending on the total combination of the reactance of the inductor, the reactance of the capacitor, and the resistance here. So this one says, consider this RLC circuit having the following conditions. So, and more following conditions. There it is. What is the maximum current and the phase constant relative to the applied voltage? And so this is a lot like that other one. Let me put those in. I will start with what's the impedance. The impedance is the square root of the resistance squared added in quadrature to the reactance from the inductor and the capacitor, where this is omega L and this is 1 over omega C. So in our case, we have a resistance of 50 ohms. And so I'll go 50 and square it. Over here, I'll do the reactance to the inductor. That is our 2 times pi times, what's our frequency, 60? Oh, that must be the famous 377. Okay, there's the omega. And then I'll multiply by the L, which is about a 0.7. And so I'm getting a 264 ohms. So I'll put it right here, 264 ohms. The reactance of the capacitor is omega, which I'll just type in as 377, times the capacitance, which is a half of microfarad, and then take the reciprocal of that. Oh, huge. 5,305 ohms. 5,305 ohms. So, unlike the last one, where the circuit was dominated by the inductor, this one is dominated by the capacitor. In fact, I don't even know if I should say the last one was dominated. There was more resistance than anything else, but there was more reactance from the inductance than the capacitor. This one's got far more than any of the other ones based on the capacitor. This one's almost acting like you just had a capacitor in it. The capacitor is just dominating this thing. So if I put these together, especially this one, 264 minus 5,305, and square it, and add it to 50 squared, and then take the square root, we get 5,041. So again, it's the inductor's taken off a little bit from the effect of the capacitor, but really this is all about the capacitor. This is such a low frequency, the capacitor is just stopping everything. And so I can answer this part by saying, okay, what is this maximum current? By saying what is the voltage, and divide it by that impedance. And the voltage was what? 170. So this is a wall plug. And so I've plugged it into the wall, 170, and divided it by 5,041. So 170 divided by my last answer comes out to be 0.0337 amps. And so there's the first part of the question. What is the maximum current? And then the other part of this is that phase constant. And so again, remember our phasor diagram. We got this phase constant by saying the tangent of the phase is XL minus XC over R. And we did this number already, so this is 264 minus 5,305, all divided by 50. And of course, not a surprise, it's going to be a huge negative number, which it should, because this is dominated by the capacitor, and the capacitor is that ice that we talked about. And so we should have current long before we get our EMF. So this is probably close to 90 degrees, negative 90 degrees, but I'll see what I get. So 264 minus 5,305, divide that by 50, and now I will take the inverse tangent of that, and I get negative 89.4 degrees. Yeah, and so it's almost just like, forget the resistor, it's too small. Forget the inductor, it's too small. It's just all about a capacitor, where we've got almost 90 degrees out of phase, where we get current before we get voltage. Yeah.
Are we going to have to know that the wall outlet is 120 volts with a max of 170, or would you just do that?
I will probably do something like this. In North America, you should know that. I probably won't give it to you. If you ask during the test, I will roll my eyes and give it to you. How's that? Yeah.
At lower frequencies, the ice effect is more likely to occur.
Right. Now remember, these two get balanced when omega equals 1 over the square root of LC. Right. Right, and that's that Goldilocks frequency we talked about, or that magical frequency. So any frequencies lower than that, it acts more like a capacitor. Anyone's higher than that, it acts more like the inductor. And the higher it gets, the more the inductor dominates. So at really high frequencies, you could really just ignore the capacitor. I mean, at high frequencies, you could ignore the capacitor and resistor, and at low frequencies, you could ignore the resistor and the inductor. But you might as well, but in this case, we got them both, and you can see it's just so highly dominated. This, yeah.
How did you get the angular frequency?
It's not a W, it's an omega, and the omega is the number of radians per time. So you take the regular frequency, and then multiply by 2 pi. So every oscillation is mathematically a 2 pi. Yeah. So in our case, it was 2 pi times 60, which is 377. Yeah. This part. All right, and then the last one I think is also like the other one. This is another preview for what's to come this week. But here we have another radio station. This is an AM radio station. It's 64 KFI. It broadcasts isotropically in all directions. It has an average power of 50,000 watts. First part of this is, I was going to say an easy question, but you haven't seen it yet, so it may not be that easy to you. What is the speed of these radio waves? Yeah, and so if you remember what I talked about, what I'm going to surprise you with on Tuesday is the same work that Maxwell did. And Maxwell was working along here, and he realized that there would be this phenomenon where the electric field would make the magnetic field, which would make an electric, would make a magnetic, which would make an electric, would make a magnetic, would make an electric. And so therefore, the information from one can be transmitted across open space to another, and we would have wireless communication. And so he was the first one to realize that we can have these radio waves. And when he went to calculate their speed, he discovers that they are the speed of light. And so besides being excited that there was something new, these radio or wireless communications, I mean, the whole idea of communicating from New York to London or from New York to Paris was just mind-blowing. And so when he discovers this in 1865, it's like, wow, this could change the world. We don't have to wait 3 months for a handwritten letter to sail across the Atlantic. We could actually communicate at some enormous speed. What is that speed? And then he calculates it and he gets the speed of light. And he gets more excited because if it's the speed of light, what does that tell him? That maybe light is a form of these electromagnetic